Well, welcome, Calc students. We are going to cover section 3.7, which is applied max and min problems. When we covered our absolute mins and absolute maxes on open intervals, it's going to be the same concept, only now it's going to be in word problem form. So our first step, once again, is always to read the problem and possibly reread. Okay. Then you can sketch a picture and label with any given information that you have. Write down an equation. Focus on what quantity is being minimized or maximized. Okay. Now, there could be a situation where they give you a second equation. That second equation is going to be used to help you eliminate down to one variable in your equation. So they might mention surface area and volume. You're going to have to pay attention to which one's going to be minimized or maximized. Is it volume or is it surface area? You're going to find the domain interval using those physical restrictions. And remember that we are in open intervals, so probably going to have our parentheses. And then, as always, we are going to solve using calculus. So let's look at our first problem. I've done it already. It's already prepared for us. We're just going to kind of go through it. So example 1, we're talking about an open box is to be made from a 16-inch by 30-inch piece of cardboard by cutting out squares of equal size from the four corners and bending up the sides. So we're having a crafty moment here. So we have this nice little piece of cardboard, and we're cutting out these squares of equal size. I know you're asking, how does she draw so well? She should have been an artist. I know. So these are all being cut out. And then what we have left, we're going to take this flap and fold it up, this flap and fold it up, this flap, fold it up, this flap and fold it up, so that we have this nice tray. Now you're probably thinking, good gravy, it can't get any worse, but yet it is. Okay, so we've got our little box here. This dimension here is that X that you cut out. Now, when you're looking at the volume of this rectangular figure, you've got length times width times height. Okay, well, this height is our X. The side that used to be 30, you just cut one X out and you cut another X out. That's where we get 30 minus 2X. Now this side used to be 16 inches, but we cut an X out, we cut an X out, so we cut out 2 X's. So that's what our equation is going to look like. Now we knew we were working with the volume of a rectangular solid, because it talked about largest volume. So largest, we are looking for that absolute max. Now we need to look at our equation. Okay, so we have X times 30 minus 2X times 16 minus 2X. So we're going to multiply all of that out. So that's where we come to here. We need to come up with our domain. We know that we can't cut out X's that are smaller than 0. It's just not possible. And we don't want to cut out squares that are 0, because then it would just be a flat sheet of cardboard. It would not be a box. So we know we have to be bigger than 0. Now, how we get our top number is we look at these guys right here. Well, what's going to cause them to be 0? This one would be 15. This one is 8. You've got to go with the smaller amount, because you can't cut out 15, because this side you can't cut 15 out of both. So you go for the smaller value. Once again, we can't have 8, because then we'd be cutting out that entire side. We wouldn't have any cardboard left. It would be a terrible box. So once we get our equation and we get our domain, then we're ready to do the first part, which is to take our limit to see if we even can maximize this. We're taking that 0 from the right side. When we put 0 in, we get 0. When we put 8 from the left side, we get 0. Now this is a problem. We remember yesterday that, might have been yesterday, it depends when you're listening to the video, The last time we did section 3.7, we learned that if it's positive infinity to negative infinity, then we absolutely know things. If it ends up going to a number, then we have to prove things. So we're going to make sure that we are ready to prove things, because this is a 0 and this is a 0. Okay? Now, what happens is, because both of those limits, let me go back just a minute, both of these limits go to 0, remember there's a theorem that we covered, it's called Rolle's. And we have to talk about our volume function, and it is a function of x. V of x is continuous on that open, or that closed interval, excuse me, and differentiable on the open. And we just found the derivative. Okay. And v of 0 equaled v of 8. That means there has to be a place where we've turned around. There has to be a place, therefore, by Rolle's, there has to be a place where my derivative is equal to 0. It's either going to be a max or a min. We will have to prove that it is indeed a max. All right, so on with the show. After we show that we've done our limits, and we have to show those limits, we're going to take the derivative, which would be 12x squared minus 184x plus 480, set that equal to 0, and we're going to solve. We get two critical points. We get 10, 3, and 12. Now remember, our domain is from 0 to 8, so 12 is not in our domain, so we've only got the one critical point. So that one critical point has to be our extrema. Okay. Let's try an example all our very own. Now I want you to be careful, because they're going to try to trick us, because look at our problem, our example 2. It says find a number in the closed interval 1/2 to 3/2 such that the sum of the number and its reciprocal is a min and is a max. Now what we have been doing has been open intervals, but remember in section 3.1 we did closed intervals. They're going to be very sneaky, so we need to be paying attention now to, is it closed, is it open? Remember, if it's open, you need to look at your limits and then do your derivative, find your critical points from that point. You may have an absolute max, maybe you don't. You may have an absolute min, maybe you don't. On closed interval, you have to find the derivative, and you will have one of each. Okay? So let's find our equation. We're looking at the sum of a number and its reciprocal. Okay? I'm going to go ahead and find my first derivative. Okay? And I had the derivative of x is 1. The derivative of 1 over x is negative 1 over x squared. Get a common denominator. It's going to make it easier for you to find your critical points. I have critical points from where the numerator equals 0, which is going to be positive 1, negative 1, from where the denominator equals 0, which is 0. Now look at your interval here. You're going from negative 1/2 to you're going from positive 1/2 to 3/2. So not all of my critical points are in that interval. In fact, this one isn't and this one isn't. Okay? Now remember, on a closed interval, those absolutes are going to happen at endpoints and at critical points. So we're going to put in our 1/2, we're going to put in our 1, and we're going to put in our 3/2 and see who's the winner. So when I put in 1/2, I get 5/2. When I put in 1, I get 2. When I put in 3/2, I get 13/16. Now they want to know, find a number in that interval such that the sum of the number and its reciprocal is a min, is a max. So they want us to find the number at which that occurs. So I have my minimum. Which one of those values is the smallest? Well, 2 is the smallest, so the number that got us there was x equals 1. B, they want that max. Which one of those is the biggest number? Well, 5/2 is. What number gave us that? That would be 1/2. Okay, so now we know we're going to have to be a little tricky whenever we're talking about absolutes. We're going to have to pay attention to, is it open or is it closed? Excuse me. Too many videos. Example 3, a closed cylindrical can is to hold 1 liter, which is 1,000 cubic centimeters of liquid. Okay, cubic centimeters, remember, it is volume. How should we choose the height and the radius to minimize the amount of material needed to manufacture the can? So we are looking to minimize the amount of material. We're not minimizing the volume. We're minimizing the surface area. That's the amount of material. Well, when I look at a cylinder, my surface area is going to be the top and the bottom of the can. So you've got 2 circles. And then you've got that cylinder part. Well, if you cut that and spread that out, that's going to be a rectangle. The length would be 2 pi r, okay, because the circumference. And then the height of the can would be the height of the rectangle. So that's what we're needing to minimize. The other information they talk about is the volume. That volume pi r squared h, that's meant to get one of these variables solved for. Because as it is right now, I can't minimize, maximize it if I have r's and h's. So this little equation here is to solve for one of them. I know that I have 1,000 cubic centimeters. I'm either going to solve for r or I'm going to solve for h. Okay. So all of this is going in right here for my h. And I want to do that before I take the limit. I also want to simplify that before I take my limits. So 2 pi r squared plus 2 pi r times 1,000 divided by pi r squared. Simplify, please. Make your life easier. Don't mess with this little nasty thing. So if I simplify that, one of my r's is going to cancel. So one of these r's is going to cancel with one of these r's. I still have one left. The pi's are going to cancel. Remember, I'm going to be taking the derivative of this, so I'm going to go ahead and bring up the r. So I'm ready. So -1. Okay. Now, to do our domain, because I need to do the domain before I do the limit, because I need to know what those values are, I know for a fact that my radius, because that's the only variable I have left, it can't be smaller than 0. Okay, so I can't have 0, because if the radius is 0, that's a terrible can. It's not going to hold anything. On this particular one, it's going to be very difficult for us to see that top end number. It's not like our nice pretty little rectangular shape. So even though we know the radius is not going to go to infinity, we don't know exactly what that number is, and trying to figure it out is going to take a lot of time. So we're just going to go ahead and take it to infinity. So we're going to do our 2 limits as r approaches 0 from the right side. 2 pi r squared plus 2,000 r to the -1 power, and then we'll do our limit as r approaches infinity. Okay, here we go. Now if I put in numbers very, very close to 0, this guy is going to 0. This guy, however, you're putting in numbers that are smaller, smaller, smaller. So this fraction, you're going to have 2,000 over a tenth, 2,000 over a thousandth, 2,000 over a millionth. That is getting really, really big. It's going to positive infinity. Okay, this little guy over here, when we're looking at infinity, this guy now is going to 0. Because as your denominator gets really big, your fraction gets really small, goes to 0. Fractions, as your denominator gets small, fraction gets bigger. Okay, so when I put positive infinity in here, sure enough, I'm going to positive infinity. That means we do not have an absolute max, no absolute max, and that's okay because they weren't asking for it anyway. But there will be an absolute min, so we will be able to minimize our material. There will be an absolute min. If we only have one critical point, that's the one we got. All right, so now comes the good stuff. We are going to take the derivative of our function. Remember, we had 2 pi r squared plus 2,000 r to the negative 1. So we're going to take the derivative. So the derivative, and you could put dSA over dt because we've got surface area there. That's going to give us 4 pi r minus 2,000 r to the negative 2, which would be 4 pi r minus 2,000 over r squared. Get a common denominator. It's going to make your life easier in the long run. R cubed minus 2,000. Okay, now we're going to need to set that equal to 0 and find out where it's undefined. Now remember, our domain is from 0 to positive infinity. When we find those critical points from the denominator, that's going to be 0. That's not in our interval. So the only one we really have to worry about is when the numerator equals 0. Okay, so subtract your, or add your 2,000, divide by 4 pi, and then take the cubed root. So my critical point, and we'll want to put that on there so they know we know. Our critical point is going to be the cubed root, wait for it, 500 over pi. Because 2,000 divided by 4 is 500. You're dividing by pi. That's our r. We know, because we did our limits, that is where our absolute min is. Now, go back up to the original problem. We need to make sure that we're answering all those questions. So choose the height and the radius. We've got the radius. Now we need to find the height. Remember that the height is 1,000 over pi r squared. So we're going to put our r in there. It's going to be pretty. Okay, now when we're looking at our pi's, when we put that in there, h is going to equal 1,000 over pi, and then we're going to take this 500 over pi squared. Okay, now you can leave your answer just like that. You do not have to simplify any further. You do need to put your units on. We were cubic centimeters, so this one's centimeters and this one's centimeters. Okay. All right, so not too bad. It's not the most attractive thing we've ever seen, but it's not bad either. Let's look at our last problem. There won't be a second video on this one. We're going to find a point on the curve from y equals x squared that's closest to the point 18, 0. Closest to the point means that we are doing an absolute min. So that's absolute min. Because we're talking about points, our interval is going to be negative infinity to positive infinity. Yes, we know it's not going to be out that far, but it's a point. It could be anywhere around this 18, 0. Closest says absolute min. It also talks about distance. So we've got the point 18, 0, and then we also have the point x, y. Well, they tell us y is x squared, so we have this point right here. So here's point 1, here's point 2. We're going to use the distance formula to help us out. So the distance formula is going to be x minus 18 squared plus, and then x squared minus 0 squared. If you simplify that out and go ahead and simplify that, you should get x to the 4th plus x squared minus 36x plus 324. Our domain is going to be positive infinity to negative infinity because we're talking about a point. It can be positive, it can be negative. I need to do my limits, so we're going to look at when x approaches negative infinity and positive infinity. when we're looking at this, we're going to look at the highest powered term. That highest powered term is going to be the square root of x to the fourth. Well, anytime you take a negative number to the fourth power and then square root it, you're going to get a big positive number. Same thing goes here. We're looking at that highest powered term. Okay. Now, when we do this, I apologize for my notation. Let me back up. We can either refer to the actual name or we can write the equation in there. So what we're doing is d of x, and I really should have my x here because that's my variable. Okay. Now what we're looking at is just that highest powered term. So we're just going to be looking at this guy right here. But we need to write d of x because we have to let them know we know we're talking about the whole equation, but that's the one that's going to drive the show. So that's going to positive infinity. Same thing, we need to go ahead and put our dx in there. And then that's going to positive infinity as well. So this tells us no absolute max, but there is an absolute min. And I will find it by finding those critical points. Okay, so looking at my derivative, okay, here's my original function, x to the fourth plus x squared minus 36x plus 324. When I find the derivative, I keep forgetting to put my x in there. It's a chain rule, so bring the 1/2 power down in front. Don't do anything to the inside. Subtract 1 from the exponent, then multiply by the derivative of what's inside. Rewrite. It looks like everybody has a 2 involved, so if I were to factor out a 2 here, I would have 2 times 2x to the third plus x minus 18. So that 2 is going to cancel with that 2 here. Any little thing you can do to make this a little bit better, please do that. And then the bottom, we've got x to the fourth plus x to the second minus 36x plus 324. Now, when I go to find my critical points, I'm going to set the numerator equal to 0 and the denominator equal to 0. Okay? And I'm going to have to use my calculator to help me find these things out. Well, when I look it up in my calculator, the denominator doesn't ever equal 0. The numerator equals 0. And use your calculator. Remember, hit second trace, go into your zeros, find them. The only critical point you're going to have is that x equals 2. Okay? And if you need help, please do this on your calculator. And if you can't find that 0 at 2, please let me know so that we can figure out together how to use your calculator. Now, they want to know the point that's the closest. That's the x-coordinate. I need to go back to the original. So to find the y-coordinate, I'm going to go back up here to the original. Well, if x is 2, y is 2 squared, so y is 4. And we're going to write it as a point, and we're going to rewrite what it is. We want them to make sure that we know this is the closest point. This is our answer. Okay? So once again, you don't have a second video. That's why this one's a little bit longer. I'll see you in class.